talk a little bit about the EDS now. So we already have the EDS program running. And if we look on it, we can see there is something called input count rate, that is how many X-ray quantums reaching the detector. Output count rate is how many we actually measure the energy of. And then something called dead time. And you see it's go all the way up to red here. And you see there's a green area there. So we want to be in that green yellowish zone. So for these kind of detectors, it is important. This is a silicon drift detector that we have here. And you want to feed the detector with, what shall I say, an intensity that is suitable. Not too much and not too little. But why this is red here is a false reading, because we have the camera on in the chamber. So if you turn off the camera view there, then we can see the real signal strength here. So, and as I said, for doing EDS, we need to be on beam intensity 15 at least to get high enough intensity. So we can see that we are about starting to come into the green area. So this is like the lower working range here. So if we want to have come higher up on that dead time scale, there's two ways of doing that. Either we increase beam intensity, or we change the parameter called process time. Process time is how much time the detector is spending on measuring the energy level of each X-ray quantum. So if you choose a higher number, it takes longer time to read. So you can, if you click on the gear there, you can change it to 6 instead of 4. Then you see, now we are on 35% in the mid-range there. So it takes longer time for it, so it will be more occupied, and the dead time therefore goes up. But we don't want to optimize, it's not the dead time that's important here. The dead time shall only be on that greenish part. So what we want to optimize is the output count rate. Now it's about 7,000 there. Go 6.5 to 7.5, something like that. That is the data we're collecting. The more counts, output counts we have, the faster it is to, what shall I say, reach satisfying statistics in our EDS spectra. So if we change the process time, it's about 8,000 here now. So if we put it back to 4, do that. You see, now it's about 10,000, about 20% up. So this means our analyst time will be 20% shorter. So we would like this output count rate to be as high as possible while still keeping the dead time on the green area. So there's no point being very high up on the green area on dead time. We want to be in the lower end of it. That will reduce our workflow time. So you can try perhaps process time 5, perhaps is best in our case here. Then we will be a little bit in the greenish area there, you see. And we still keep a quite high count rate. So, and the other way to increase the dead time is, of course, increase beam intensity. But now we have set up the whole machine and everything King's beam intensity 16. So if we increases that, we need to do column centering, stigmatic correction, and things like that. So and that's beyond the scope of today. And I don't think it's necessary either. But I mean, it's good to emphasize this thing that, what should I say, the proper setting depends on the user case. And as I said initially, it is not that beam intensity 1 and highest resolution is always beneficial. Many times people think high resolution work is what they're doing, but then they are on like 10,000 in magnification. Right now we're on almost 4,000 in magnification. This is very low magnification work in electron microscopy business. But you need to sort of, what should I say, get some kind of experience what is considered high resolution. High resolution is when you're starting to want to have a spot size that is in a few nanometer maximum. Most likely you want it to be below 1 nanometer. That is high resolution. So if you continue to look on that screen up there, this Oxford EDS software is, what shall I say, very pedagogical in its workflow. It has, what shall I say, a top row of tabs, like arrows, and that is the workflow. So further to the left, you choose the detector technique, and it says EDS SM. That's the only thing we have on this machine, so we know we never change that. And then it comes to what type of measurement do we want to do. Is it point measurement, line scan, or a map, and so on. And then you just follow the tab order. So we're going to start with a point scan first, and then it says describe specimen. And yeah, you can write a note if you want in this, but the most important thing is that if you go down, you can choose if it's coated. And our sample is actually coated with iridium, and it's coated with 10 nanometer iridium, so we can choose that there. And if we also have several samples, we can see this drawer structure to the left. It says specimen 1 now and site 1. So if one has several samples, one can right-click on specimen 1. Here, one can right-click, and you can name it. So this is sample 1 or something like that. Yeah. So then we just continue the tab order. Go to the next, scan image. So what is scan image? You can also see that there is this gear icon on all tabs. The gear icon you can click on. Here. And the gear icon shows, what shall I say, parameters for scanning an image. Now it says 2000 pixels. And instead of scan time, it says dwell time. That is the time it spends in each pixel. So if you choose a higher number, it takes longer to scan, basically. So it's just the inverse of scan speed. But here we can see it takes about 20 seconds to get the image now, which is fine, I guess. When it's, and it says number of frames also. That is the averaging. We want 1. But one important thing here is that it says input signals, and it says SC, which is ticked, and it also have BSC. And this is not correct, because this EDS software thinks that the secondary electron detector is always connected to channel A on the microscope, and the BSC is connected to channel B. But in the Tescan microscope, you can choose whichever detector you like on whichever channel you like. So in the EDS software, it would have been more correct if it said channel A and channel B. So even if it says SC in the EDS software, it is the channel A it refers to, which will be the backscatter signal. So no, so you keep it on SC and click on that. We only want SC. Yeah, so otherwise you get 2 images. You can close that and click start, the green button there. So then the EDS computer takes over the control of the electron microscope and makes a scan image here. And this will be the thing that we will orient ourselves in the EDS analysis. So this is our map. We're sort of going to, what shall I say, test for different elemental compositions. So this is the image. So if we just continue the tab order to acquire spectra. So here, since we are in point and ID, we have a bunch of options here. Here it's acquire spectra from a point. I acquire, what shall I say, the sum or average, or what you want to call it, from an area. And it's good to make a little bit, what shall I say, talk on that subject also. A general thing about EDS measurement is that it is too easy to do EDS measurements. So it's so easy to make mistakes which fools yourself. That is the problem with EDS. And for example, one very silly thing is that when we're scanning here and get the scanned image up there, now I have been talking for 1 minute or so. So if the sample is poorly coated and is charging, that means that that image is not where we are looking on right now. This was the area we were looking 1 minute ago. But we don't know that since we don't check, right? So this is the problem if you have a charging sample. In EDS, it's like game over. You need to have a proper coated sample or a sample that needs to be coated. You don't want to have charging because it will since EDS scanning usually is time consuming also. If you're scanning for 20, 30, 1 hour and you have a little bit drift, then when you come back, you are actually measuring something completely different. So that is one issue with this. But in this case, we don't have any problem with that since our sample is rather good coated. But then it's the thing, why should I choose a point and why should I choose the average of an area to collect the data from? Then we come back to this thing about, carbon contamination of the surface. Since the electron beam is illuminating the sample, organic residues inside the chamber will be ionized by the beam and deposited onto the surface. That means we'll start measuring carbon on the surface. Even if it doesn't contain carbon, we start measuring carbon. And the longer the beam is in one point, the more carbon we will start measuring there. So if we're scanning on one single point for a long time, that means we will build up a lot of carbon on that area. And we will have a lot of carbon signal in the spectra. But if we scan a bigger area and take the average of that, then since the beam is moving around, there will be less carbon at each place the beam scans. So we reduce the carbon issue. Another point of doing the area thing is that if the sample is beam sensitive, we don't start to drill a hole with the beam in one area. We spread out the energy on a larger surface, which is also nice. A third case is that the X-rays that is emitted, one should say like this, in EDS it is very important that the sample, from a theoretical perspective, you want it to be homogeneous, no heterogenic or anisotropic structures and things like that. It should be completely homogeneous. The surface should be mirror polished. No geometrical artifacts on the surface. That is the ideal conditions. If you move away from that, let's say you have a crystal grain. Depending on the angle of that crystal grain, if it's facing the detector or facing away from the detector, certain X-rays will be enhanced and certain will be suppressed. So by accident, if you're scanning 2 points, one point can be on a grain tilting away and one point tilting towards the detector. And then you get 2 different intensities of the X-ray spectra there. And it might lead you to make wrong conclusions saying in this area we have a different composition and compared to this area. While in fact it is a geometrical artifact. So by doing the averaging, we tend to eliminate that because we get some more like the average of the sample. So let's try now. If you we can do the point first. And then we click on the outside here first. Like that. So now it starts to scan outside those crystal grains. And we see some spectra down there.
Carbon.
You see a lot of carbon, right?
It is a wood sample.
Yeah, I mean, it's a wood sample, so it should contain iridium from the coating. It should contain carbon and oxygen, right? And even if it doesn't contain carbon and oxygen, if you sort of modeling like a steel alloy all steels have carbon content below 3%. Cast iron, I think, is like 3%. But if you're measuring the carbon content here, you will measure like 15% and things like that. And that is caused by the carbon contamination of this in the chamber. You also have oxygen contamination. So carbon and oxygen is very tricky to measure. So click on top of the big crystal, and you can also take the small crystal also that was below there. And then we can see they get different colors. So the white is something that has been finished measurement. The yellow is ongoing, and blue is in the pipe, so to say.
Yeah, it was a silicon.
Yeah, so we can see directly in the X-ray spectra, it identifies it as silicon, which can be explained, I guess, because you use probably silicon carbide paper to grind it.
Yes.
So it can be remains from that. So it should be interesting to see what the other one is, that it also is silicon carbide. Here it's some other thing. Or perhaps sodium. We will see how it evolves.
Maybe it's salt, like you said. Aluminium. Potassium.
Yeah, it's interesting. We see a lot of different compounds there.
Yeah, I didn't see any of those in my previous sample.
Yeah. But this is nice. I mean, these are all a bunch of metals at least. And they are, of course, heavier than carbon and oxygen, which is why they are brighter in the backscatter electron image. So, I mean, the backscatter detector is like the poor man's elemental analysis. We can say if it is a heavy element or lighter. But EDS, we get exactly what kind of element it is. So let's continue to confirm. You see the arrow here has a little bit question mark on it. So what we can do now is we can go in here and choose. So here it's very interesting. It says sodium and zinc on the same. And the EDS software do its best and look on the database to try to match up the characteristic X-ray peaks to corresponding to each element it has. And we can look on what kind of database it uses. You can see that here. So here it says it uses the standard-sized extended set. So this is the default set that you should use. If you use a low voltage, you can go and use a 5 kilovolt set here. If you have voltages that is less than 15 kilovolt. The reason for that is then it only uses the database of the characteristics peaks in that low energy range. Because if you're using a too low energy, we cannot excitate all characteristics X-rays. So it is on the correct set there. It also has deconvolution of elements. So if you want to remove elements from our spectra, that is called deconvolution. So then we can do that. And it's quite common you want to deconvolute carbon and oxygen because you always have that as contaminants. And then you can do that. It also says that it normalizes the result. That means that if we do quantification calculations on these spectra, it will always add up to 100%. That is what normalization means. That sometimes is not perhaps so smart to do, because sometimes you want to know, where shall I say, how much of the X-rays that are lost, one can say. So let's say we are measuring lithium fluoride crystals. The EDS in default configuration, as we have here, cannot detect lithium. Bohr is the lightest element that we can detect. So if we are measuring lithium fluoride, lithium we cannot see. It will be invisible.
Yeah.
But from a stoichiometric point, we have 50% of the atoms is lithium, and the rest is fluoride. So if it says 100% fluoride when we measure lithium fluoride, might not be so smart to have that option. We would like to measure like 50% atomic wise
Yeah.
on that. So it's good to mention these things, that you keep track of what you're doing. And as I said earlier, EDS is so easy, so you easily make mistakes also. And you as an operator is the one that need to understand this, because you are the professional. When you tell your professor that is not having any electron microscopy experience, you are the one that needs to do the proper decisions and judging your data correctly. Mm-hmm. But here, if I double click here with the question mark, we can get from the table the most likely candidates. So it says sodium and zinc are in the same region, right? So both matches that peak.
Yeah.
But why does it say that it is both sodium and zinc in our case? Well, it actually uses characteristics X-ray peaks in higher energy range. So if I go up here, I thought I saw it somewhere here. There you see. Zinc also has a peak at 8.6 kilo electron volt. But sodium doesn't. And it also has a peak here at 9.6. So that makes it very convincing to me that we actually have zinc here.
So no sodium?
Yeah, the sodium case, if we look on the sodium, you see sodium only has one peak there, right? If we also look on our board here, you can see sodium only has K alpha, right?
Yeah.
So, and it overlaps that zinc peak. So if we look on the shape of the peak, here I would say we are on some kind of threshold. It's a very unfortunate that sodium overlaps the zinc. We definitely have zinc.
Yeah.
But the question is, do we also have sodium? It could actually be the case that we don't have sodium here. I would like to have, if we have sodium and zinc, that peak will be a little bit broader, right? We cannot resolve them, but it will be a little bit broader. So at this stage, I would like to see other data that it contains sodium. In this case, I would say it definitely contains zinc. It could contain sodium, but I'm not sure it actually do that. So let's say we don't believe that it actually contains sodium, then we can actually change this manually here. So if I double click here, then it makes that red. So now we excluded sodium and deconvoluted it from our spectra here.
Yeah.
And you see here, one can also use, we can compare to spectrum 1 if we want here, which is our reference spectra outside here. And we can see the red one contains carbon and oxygen and region.